So now let's talk about boundary conditions. Let me just mention it now, even though I talk a little about it a little later in the slides, is load cases. When you solve a finite element problem, actually most of the effort involved is doing the decomposition of the global stiffness matrix. And actually solving for different boundary conditions doesn't take that much more work. So if you have multiple boundary conditions, and actually this is typical for most design problems because parts are loaded in several different modalities, it makes sense to solve the system once and then apply several different boundary conditions. So you'll have this notion of multiple load cases. And Nastran supports that, so I'm going to talk about that now. So the first type of boundary condition is boundary conditions that prescribe nodal displacements. Typically, we're going to just have simple fixed conditions. So certain degrees of freedom of certain nodes are going to be fixed. These are going to be done by what are called single point constraints, SPCs. And the card itself in Nastran is called an SPC. In fact, this is a pretty common terminology. Most softwares have something called SPC, and in the finite element community that's assumed to mean a single point constraint. So the first field is the single point constraint. The second field is the set ID. So again, one load case might have multiple single point constraints associated with it. So that set ID that's in field 2 is a sort of a non-unique ID that groups multiple SPCs into one SPC set, if you will, that can be then specified in a particular load case. So here we've used 2. You could use 1, but I just used some different numbers to show some non-overlap. The third field is the grid at which you're defining the SPC. So here are the 2 nodes, 1 and 3. The fourth column are the degrees of freedom that are being fixed. So this is 1 or more integers from 1 to 6. 1, 2, and 3 correspond to the translational degrees of freedom in the x, y, and z direction. And 4, 5, and 6 correspond to the rotational degrees of freedom in the x, y, and z directions, respectively. This is about the coordinate system for the node. Typically, again, for these problems, we're going to be using the global coordinate system. But, again, if in your node definition you specified an alternate coordinate system in field 70, field 7, then that would mean that the constraints are with respect to that coordinate system. So that lets you do things like, if you wanted to constrain it to slide on an incline, we might do something like that. It's a good trick to know. But typically, again, we're going to use global coordinate system. So these are global degrees of freedom. And here we're fully fixing all degrees of freedom, all translations and all rotations. Field 5 is the value. And so here we're going to set them to 0. You could set them to 1 or whatever, but we'll set them to 0. And then actually you got 3 more fields, which lets you put in another grid point, another set of degrees of freedom, and more values. And actually I could define these 2 SPCs in 1 line, but I usually just do it in 2 lines to make life a little bit easier. I guess, I guess they figured you have this 3 extra fields, so why not make it a little more terse, but I usually put them on extra lines. So it would be the same. You could have actually put 1 line where field 6, 7, and 8 would have been fields 3, 4, and 5 on the subsequent line, okay? All right, so that defines the single point constraints. The last thing we have to do is define the nodal force, okay? So the card force is the one that does that. Again, these are used for 1 or more load cases, so you need some way of organizing multiple forces. So column 2 is the same load set ID. I'm using 10 here to group the forces. The next field is the grid point. You can actually have a different coordinate system to define the force, but again, we usually use a global, so field 4 is blank. Field 5 gives you the magnitude of the force, and then fields 6, 7, and 8 give you a direction of the force. Now it turns out in Nastran, I believe, I have to remember, some do it differently, that in fact, if your direction is not a unit vector, let's say our direction vector was of length 2, like for example it was 2, 0, 0, then we would in fact be applying a minus 10,000 pound force. Okay, so the magnitude of the direction vector scales the force magnitude. To keep it simple, I usually try to always use a unit vector, so then it's not really an issue. You don't have to remember whether it scales or not. And here it's a force in the minus x direction, so I use a unit vector of 1, 0, 0, and then a magnitude of minus 5,000. So that puts a minus 5,000 or 5,000 pound force in the minus x direction. Okay? All right. So here's kind of the cards that we've talked about all laid up. They would all be in a single text file. I know it's hard to see on the video, but those are all directly copied out of that myfirstnastran.bdf file. That's, you can get off of WebCT, I mean Blackboard. But here just to show you how things are related. So the grid points are referred to in the element connectivity. So here you can see, global grid points 1 and 2 define the connectivity of the first element. Global grid points 2 and 3 define the connectivity of the second element. So those numbers have to correspond. Also, the part IDs have to refer actually to property cards. And here you can see the properties, the 2 different property cards for the 2 different elements. And again, there's 2 different property cards because they have different cross-sectional areas. The material IDs, now they're referenced from the property card. There's one material in this model, so they both use the same material ID, but they have to uniquely identify a particular material card. So this just goes to show you that you can't have multiply defined grid points, or each property has to have a unique ID, and same with each material. Okay. All right. Actually, I probably should have done it to begin with, but this is in the top. I'll talk about this later or now because I think it makes more sense. This is the executive control section, and then the load sections, the load case sections. Okay. So for us, the executive control section really is just going to be one line. It's just sol 101. There is no field width associated with it. You can just put SOL space 101. That's fine. That tells you that you're using a Nastran, a linear elastic static solver 101. Okay? We'll maybe do some dynamics problems, and I'll tell you which solver we use for that. I believe it's solver 108 or something, depending on if we do modal or dynamic response. The next are the load cases. All right, so let me talk a little bit about this. We have one load case in this problem. I probably should have put in 2 load cases just to illustrate the difference, but we just have one load case. If you had 2 load cases, you would have basically a duplication of that subcase line and the following lines. All right? There's a title. That's the title of the model itself. You don't need that, but I think it's kind of nice. And actually, I think there's a subtitle, subcase title you can use as well. But here we have one load case. That is subcase 1. It's using the SPCs that are defined by their unique set 2 and all the loads that are defined by their set 1. So if you go back up here, oops, you can see, right? Well, actually, I'll get to that in a second, so let's go back here. Then after we define which SPCs and loads we're going to use in that load set, then the next 4 lines determine the output. I suggest you always use this. This is pretty easy. This just writes all the displacement results, all the SPC force results. Those are the reaction forces. And then it also writes all the stress and strain results, including the von Mises effective values. Okay? But you can look at the manual, and there's other things you can output into different formats if you want to. Okay, but this will give you most of the outputs that we need for our problems we're solving. And again, each load set could have different outputs. Okay, but I suggest you just use this for all the different load sets you have. Okay, there's no field width here, and these cards are required. Okay, so again, you can see here, for example, for load set 2, we're using SPCs that are ID'd 2. So here you can see that those are referring to that second field in the SPCs. If you had some SPCs that were in, say, another set number, 3, they would be ignored for that load case. And likewise, for loads, you're using the forces that have set ID, load set ID 10. So if you had multiple forces with set ID 10, you would be using those. Okay? Okay. Well, at this point, we're ready to solve. So let me just solve, and then we'll talk about the output files, okay? So when you go to run Nastran, this is actually my desktop, so this is, you know, the Windows machines and etc. When you go to run Nastran, it's really actually kind of boring. So if you go under my programs, you can see there's all programs. There is a section called MSC software, and this is in the remote desktop and also in the computer labs and in my desktop. There's 3 different modules typically here: Atoms, Nastran, and Patran. So Patran's a preprocessor, and Atoms is a kinematic software. Well, we're using Nastran. You can see actually this is called MD Nastran. If it says MSC Nastran or MD Nastran, it's fine. It's the same thing. And then you can see here there's really just one program to run. It's the executable for MD Nastran. So if you click on that, what you get basically is just a file directory. So this allows you to pick an input file. That's all there is. It's not any other fancy graphic preprocessor or anything. All this does is select the input file and it runs it. So I forget where the heck all these things are on my computer. I think it's in a local disk, which is local disk C. I have to get this off my drive, so I forget where this is. Is it this one? No, that's the local of the remote one. Let's see. Maybe it's one of these clients. See? Ah, here it is. Okay, so this is actually my Mac drive, but you know, you need to figure out some way to store your files. Okay, so you need to make sure you have read-write access to the directory where your input files are. So here's my input file I want to run, my first nastran.bdf. Just pick it and then hit open. When you hit open, you'll get this window. There are some keywords like that will allow you to control how much memory is used, so on and so forth. The files are outputted as well. But typically we'll just leave those blank. If this is the file you got, your input file, just hit run, and now it's running. In fact, if you listen closely, there'll be a beep when it's done executing. It won't take too long. It doesn't really put any status out to the screen. Let's see. Should be any second now. I think it's done. The beep doesn't seem to be coming through, but I think it's done. But you'll hear a beep. Now, it's the same beep whether there's an error or not. Okay? When you run these programs, what you're going to almost always find is, you know, the models, when you first try to run them, there will be an error. Okay? And we'll talk about how to solve those. So don't expect that you can just write an input file and it'll always work right off the bat. Allow time to debug the input problems, and then once you debug the input problems, then you have to make sure that it runs. Sometimes you even have errors, say, with respect to how the boundary conditions are solved. So they might still run, but it gives you the wrong answers. Okay? All right. So when it runs, it'll generate these files. You can see all these files here were generated by Nastran. Actually, this one's a duplicate. This is an old one. These are the ones that are generated by Nastran. An FO6, a log, an FO4, a dball, and a master. The most important one is the FO6. Okay, that's going to have your results or any errors. So let me take a break here, and then we'll do a third video that shows how to interpret the results. Okay, but basically, if you have any errors, they'll be illustrated in the FO6 file. Okay, I should have probably had one that has an error, but always open the FO6 file. If it has an error, look at it closely. That'll tell you how you have to modify your input file. It's usually relatively obvious. There'll be things like, grid point not defined in an element card, or you specified some set in the load case that doesn't exist, or it's not unique, or something like that. Okay.